Thank you very much for having me. As Alex mentioned, it's a great honor for me today to moderate this panel on mastering hard-to-print materials and geometries today. And with me here today, we have three excellent panelists from industry. I will introduce them just very briefly, and they will say something to their designation within their companies themselves. So first up, we have Anna Saylor from EOS. Then we have Matt Karesh from Velo 3D and Christoph Seifert from AMCM. Thank you very much for being here today, and go ahead with your introduction.
Thanks. I'll start, so I hope you can hear me okay. Yeah, thanks, Tim, for the short introduction. My name is Anna Saylor. I work at EOS, an Additive Minds consulting group. So we support customers with consulting projects, application development projects, and I'm working mainly in the metal development topics. My background is in aerospace, so I've been at EOS for the past 2 years, but prior to that, I was doing process development, qualification, and yeah, trying to get some aerospace parts into production and aerospace in the US. So happy to be here on the panel today.
Thank you very much.
And my name is Matt Karesh. Can you guys hear me okay? No. So I lead the technical business development team at Velo, and so we work with customers to educate, work on their applications, consult, things like that. My background is, mechanical engineering. I did a couple of years work in power generation. From there, went to aerospace, kind of like Anne, and worked on commercial jet engines for a number of years, and then got into additive through GE. Got to experience laser powder bed fusion, binder jet, and electron beam. So I've dabbled in kind of the three major modalities, and then have been at Velo for the last 2.5 years. Thanks for having me.
Hello, my name is Christoph Seifert. I'm working for AMCM, which is Additive Manufacturing Custom Machines. We are a sister company from EOS, and our task is to modify, customize machines, or also build machines completely new, based on customer request. I have a background in metallurgy and materials processing, materials analytics. And I had been working for 5.5 years for EOS as process developer, and now I joined AMCM to trying to develop these new tools and functionalities.
Good. Thank you very much for this nice intro. So as I mentioned, the panel today is centered around hard to print geometries and materials. So this is still kind of fuzzy. What is hard to print? So what would be interesting to me is, what do you consider hard to print geometries and materials? Probably Christoph, you go first because you finished last for the intro.
So I think you can differentiate this into part properties and their challenges, and material properties and their challenges. And part properties beginning with shape, dimensional accuracy, or the pure size of things, like very tall parts or thin walls, for example, complex structures. And the other side is the materials, with crack-prone materials, where you might want to change the processing route with several types of tools, or also the overall heat management within the build job.
Yeah, so I think I have a little bit of a different perspective. I think, it's not incredibly hard to figure out how to print one geometry one time. With the right work and supports and build strategies, you can figure that out. From my perspective, the hard thing to do in additive, and I think from the industry as a whole has suffered from, is the repeatability. And so, you can print a hard part one time, but can you print any part over and over again on any machine, regardless of where it's located? And again, I think being able to do that, or the lack of being able to do that widespread throughout our industry, is what's held us back from seeing I'll say, general or widespread adoption in production applications.
Yeah, really great points from both of you there. I think one other aspect to add on top of that makes it challenging to build parts is when we're talking about qualification, right? So like you said, Matt, we can build one part one time. We can destructively test that. We can do CT scanning on this one part. But how do we actually qualify that so that the next time that we print it 3, 4, 10, many more times, that we understand and have completely characterized whether it's the material itself, the geometry, and also what happens when we change part of the geometry. What does that mean for requalification? Do we have to do a whole full suite of qualification on that part? Can we do some subset? This is really what is a challenging aspect as well.
Yeah, thank you very much. And I mean, Anna, you mentioned it, you come from industry yourself, so you know probably some of the pain points you have when you want to implement AM in production. And you mentioned within Additive Minds your focus is on consultancy. So how do you aim to actually help customers from industry using AM more actively in production? Because I could imagine that there are different kind of customers, like very experienced ones that have several machines running, and other customers that are probably just starting. So what's your turn on that?
Yeah, and it's interesting, coming from being working in industry and working on different, additive manufacturing OEM machines. And then coming to EOS, I really have the feeling that, at the company that I was working at, and I think a lot of EOS customers and even, people that are building parts in additive, there's a lot of expertise that is actually really difficult to share throughout the industry. And I really only understood that when I started working at an OEM and I started seeing not only a lot of the difficult, hard to print components that I was trying to build, but then I saw a lot of different examples in a lot of different industries. And so, yeah, first of all, that was really mind-opening for me, and to say, okay, I thought I was an expert, but actually there's so much expertise that, I wasn't able to get that we have within the 30 years of EOS as a company. And so for me, in my role, and what's really interesting to me is trying to bring a lot of that expertise to the people that already have machines who, in some cases, they may already be experts in their aerospace, in their medical applications, but there really are creative ways that we can use machines that, in standard configurations that require a little bit of creativity, and this is really what I try to bring to my customers. My 2 years of experience at EOS, my own experience as a customer and what really customers need, but then also the 30 years of experience of my colleagues, which I would say it's a little bit underestimated how some small changes or small aspects of how we use our software, our materials, processes can really have a huge impact where people are already experts in that field.
Great, thank you very much. And I mean, it basically goes a bit in the direction of Matt as well. I think as Velo, you've started pushing this whole perspective of having more sophisticated control and data preparation, but now also trying to get the machines more reproducible for production. So I could see I think there's a lot of similarities in a way, but probably you can tell us a bit more how you see all this aspect of taking complexity out of getting each and every machine qualified.
Yeah, so I think two aspects to that. I think we spent a lot of time in kind of undoing some of the things that the marketing industry or the marketing machine of the Velo or the additive industry has done. We made a lot of really big promises, and we didn't live up to them. And we created this uphill battle for ourselves that a lot of times when we engage new customers, we have to unwind some of that. They have these expectations that are unreal or unrealistic. And so, we have to sit down with them and re-educate them. This is what this technology can do. This is what it's for. It is not to replace your very simple casting or machine. Like, it is not a one-for-one replacement, right? It's a tool in the toolbox to do certain things with. And so we need to use it appropriately. And then going on the kind of repeatability side of things, what we're really trying to do is democratize the technology. And I think, Anna, you said it really well. There's these pockets of experience, and to have really good success in additive, it's almost a prerequisite to have, like your PhD process parameter or material developer on staff, which again, I think is holding the industry back. And if we can figure out a way, to democratize the technology so that people can bring the technology in-house and they don't need that incredibly deep expertise, to stand up their supply chain, and they can, do that like they would any other machine tool, or go scale outside without, having to have these crazy lockdowns and IPs and things like that. It would do the entire industry a huge favor.
Yeah, absolutely agree. And I think to see more companies in production and not only in doing very expensive prototypes of one-piece prints will certainly help the industry as a whole, and also build trust in what the technology can bring for production in different industries. So, Christopher, you, it's basically a bit of the other end of the spectrum. As you mentioned, you within AMCM are more going in the direction of custom machines, specialized equipment. So probably for you, how do you see the role of the equipment itself to allow printing of more challenging geometries or more challenging materials? I mean, when you go to the AMCM booth, I think, or everyone has seen these huge rocket nozzles, which just in size are difficult, but probably also in terms of building the machines for them are very, very challenging.
True. So we see ourselves maybe more as enablers. So we implement new hardware tools or also software tools, trying to make new processing possible. And before we can talk about this fancy and interesting stuff, I have to agree to you guys. You have to have a solid foundation. You have to have a sturdy system where you know what it is capable of, which you have under control. Mm-hmm. And this, for example, starts with heat management. Yeah. So also for reproduce the part always in the same way. Get your system stable against any heat up, like the optics, the machine frame, the axes which are leveling the parts. Avoid any recoder contacts and stuff. This sounds all a bit boring and like from yesterday, but I think this is in some cases still challenging, and any improvement on this helps to leverage this technology in general. Beside of this, we also try to do this enabling stuff where we really get into new terrain, like make a previously non-laser weldable material happen. Could be with an specialized heating system, heating from the build plate, heating from the top. Could be with new laser profiles, especially with the nLIGHT laser, for example. Having a different intensity distribution might allow us to change the solidification behavior. But again, if I change this in the process, I need to ensure that I understand what we are doing there, that I know that I can apply this in any area of the part in the way that the part properties are under control. And this is the challenge with any new toy on the market.
Yeah, I mean, I agree. I also come from engineering, and having a solid base for a machine is always fundamental in doing all this tricky and fancy stuff then. So without that, you won't probably be able to do it one time, as Matt said, but not do it hundreds or thousands of times. I mean, another topic that I find very interesting is that, especially when you look at Formnext, like the last 1 or 2 years, there's been a lot of innovation coming from the software side. I mean, I have the feeling that the machines are coming to a certain level, and then still there's a lot of potential in software, especially when it comes to control, when it comes to data preparation for these challenging geometries. And I know Velo is working on it. EOS has their new solution for Smart Fusion. So what's your take on that, using software to make most use out of the machine, so to speak?
Anybody?
Go ahead.
So, yeah, to your point, I see a lot of software solutions out there, and I think the three of us can kind of throw stones because we're the machine OEMs. So it's easy because they can't fight. But my perspective, and people may not know this about Velo, we actually started as a software company, and the intent was to be a bolt-on solution to existing machines to make them better and make them easier. And what we found was, if you weren't inherently designed into the architecture of the hardware, you couldn't control the hardware in the way you wanted to. So, and again, I'm biased, right? Because I'm a machine OEM. But I see a lot of these third-party softwares, and my biggest concern is you're going to be limited by your ability to actually get to the fundamentals of the hardware and control it. That being said, like, the machine OEMs are also working on software. It's incredibly important. And I think probably the most important piece that everyone is working on is the in-process monitoring and trying to connect that back to part quality. So, like, I mean, you can go on forever about that, and all the different entities that are working on it. At Velo, you know, we built in a ton of metrology to first and foremost prove to ourselves what we were doing was working, because it was, you know, it was pretty crazy. We had this non-contact recoder, then everyone's, how do you get a 50 micron layer without touching the powder? So we had to prove it to ourselves. So we had to put the measurement capability in there to do that. We, I'll say, got lucky in that by putting all that measurement, that metrology into the system, we kind of fell into the ability to measure a ton of other stuff about the process and give really good feedback on the process health itself. And so we're just digging into, like, how deep can we go on that information, and what can we get out of it, and really what benefit can we bring to the customers in terms of, like, getting rid of or reducing non-destructive testing and things like that. So I think it's a call it the Wild West of additive. If additive isn't already a Wild West, the next Wild West of additive, of figuring out what we can do with in-process monitoring and how that takes our industry again to that next level.
Yeah, I have to agree that without having full access to your hardware, the best software will probably not be useful for most applications. I think that's actually an excellent transition to what you guys are doing with the Smart Fusion at EOS, using monitoring, but also using data preparation to, for example, get rid of support structures. But probably, Anna, you can give us some more insights into that.
Yeah, certainly. And yeah, just to touch on the point you just mentioned, Matt, I do feel like software is kind of, the next, you know, we're so far into the development of the additive manufacturing industry that software is kind of this last, thing that we can squeeze out and start to tweak, optimizing trying to get as much information from the build while we're still building parts, whether that's to monitor the quality of the parts. One of the ways that the EOS has developed to do that is with this closed loop Smart Fusion technology. This is kind of one tool in our toolbox that allows us to control the areas where we see overheating when we're building parts, so that we can avoid using as many support structures. We can avoid overheating our parts if we're building really, really tall. So this really helps, with some of these challenging geometries to be able to have more control over the parts that we're building. But I would also say, going back to my previous point, this is a tool in our toolbox. It's not some magical button that will fix all your additive manufacturing problems. And of course, we're still beholden to all of the challenges of particular materials. And of course, we can't overcome physics of something. So if you have a certain difficult to print material, you can improve the way that you can build that material. But of course, we still have physics that happens to get in the way of building these parts. But despite that, yes. So the EOS solution to and of course this always comes back to cost per part. So if we can avoid building parts with supports, we can reduce the build time of our parts. This eventually will feed back into our business case, which ultimately is what is important to additive manufacturing users.
Thank you very much. I mean, we now dug very deep into how we can make use of the machines that are already out there. But you, Chris, have also mentioned making special machines is about making them more flexible. And I mean, we are obviously on the nLIGHT booth. They are really pushing this flexible beam shaping technology. Where do you see the potential of actually adding even more flexibility to these machines? I mean, both from software and hardware side. It helps a lot with having even more process strategies, degrees of freedom, but it probably also makes it harder to find the right setting for each and every application.
Well, first of all, it keeps us busy, which is a good thing. No, I can directly connect to the previously spoken words. You are like a kid in the toy store with all the flexibility and possibilities. You have to focus on certain strategies. You have to kind of pull out the hypothesis, what you want to achieve with a new tool. And then you have to check if there is a potential with it. With this intensity distribution tool, like the nLIGHT laser, we have an impact, or we can have impact on the shear spot size, first of all, which is pretty obvious. You could then hopefully run wider weld tracks, have more spread or like more hatching speed. You achieve higher build rates, but you could also aim for higher scan speeds, for example, using this intensity distribution to calm down the melt pool behavior. As a result, you might have then the effect that you change the solidification behavior as well. Can be positive, can be challenging. You might have a benefit for some materials which profit from a pretty fast solidification behavior. If you scan fast, maybe, and you kind of quench in properties into the material. So lots of stuff to do there, but you have to to create a package out of part, material, plus how to process it. This is your task, and then you have to check how this all works together. Also could be, for example, shallow melt pools for low overhangs. This then gets in connection with the software solutions, and then it gets very, very complex. So first get the process behavior right, then combine it with other tools, and yeah, the possibilities seem to be endless, and we have to find our way through these waste possibilities.
Yeah, and I mean that's very true, and you have all these opportunities and all these degrees of freedom you can use, but you could also argue the other way around, that all these lasers you add and all these features as beam shaping that you add makes it way more complex for users to actually get into the technology, and probably just want to print nice parts without having to set hundreds of parameters to get it right. So any thoughts on that? How to bring down the complexity, so to speak, in additive manufacturing?
Yeah, I think I want to add on to his comments of, I think we're put in a really hard position as OEMs of, there's all these new technologies and features and beam shaping, right, that we can go after and we can change things. But at the same time, the adopters, the end users, right, they've qualified these processes, and there's numbers that have been thrown around, you know, call it 2 years, $2 million to go qualify a material for additive, and then you change one parameter and you have to go do that again. So we're kind of stuck of people want lower cost, better quality, whatever, surface finish, geometric complexity, but we go do that and then they're like, I can't adopt that because I qualified this. And so, you know, we're in a bind of, do we go innovate or do we, you know, kind of pick a place to stop and go deep? And I don't know if there's a solution there, but it's certainly something that we struggle with internally of where do we go invest in R&D and push the boundaries versus, you know, just stay in one spot and focus and improve.
Yeah, I mean, I agree. Especially certification can certainly be a stepping stone for some applications because it's just too hard to recertify part or process that you've already certified. Good. I think we can transition, also open to some questions from the audience as well. So if you have any questions, just feel free to raise a hand, and then we. Everybody happy?
Everyone loves your questions.
Okay. Good. I mean, then we will just continue as as we did before. You were also already mentioning, Matt, and I think that's a point we are all confronted with all of the times. It's mostly 3 points: cost per part, quality, and reproducibility. It's really, really high targets that AM is confronted with, and also in terms of cost targets. So what's your way forward to actually get into another direction, see how we can get new applications for AM probably, because as you mentioned, just printing cast parts is probably not the way forward.
Yeah, I think it's a balance, right? It's like a piece of it is an education piece where people need to understand how and when not to use the technology. And then from our perspective, you know, we can push the innovation and push the throughput and push the quality. We do have to simply deliver on, you know, what we've originally promised of this is truly a production technology. And that means you bring up a machine, you print a part, you can do it again and again on that machine, but you can also go to other machines and also get the same result. Because if we can't do that, then no one will have the confidence to adopt. So it's a multi-pronged approach, if you will, of, you know, bringing the customers up to speed of what is possible and what we're capable of doing, and then delivering on the original promise, plus bringing new productivity improvements, if you will, without necessarily compromising, which is a challenge, right? People want to go faster, but they want better feature resolution. Those two don't typically go together. So trying to find the balance between all those different things.
And I mean, I think in the last years, or as I experienced it, the AM industry as a whole was more or less living from these pilot applications. So the last years was all these rocket applications, and you're all very active in that field. But Christopher, as you mentioned, you are always designing your for the specific application. So where do you also probably see potential markets for the future away from space or aerospace, where we already have seen plenty of applications where it can be very useful?
Yeah. So with the trend towards big machines, this is also like maybe a door opener to new components. We see these big titanium parts or Inconel parts for potentially for gas turbines, for airplane engines, things like this. This goes then all again wieder to is the technology trustworthy? Is it reliable? Will it make a business? Yeah, like Matt already said. And this is something where I see a lot of potential if maybe sometimes there's also the right material. So let's think about maybe structural parts in airplanes. If we would manage to validate the whole processing, we might also need a new material. For example, the old RSI10MG, it's a casting material. Maybe it's time to get the forging aluminum ready now. Get down with the cost pressure. By all means, it's not only the material price, the machine price and stuff, it's also the side costs of the machine where you can still improve. Like making more clever depowering solutions, making more clever filter solutions, things like this. And if we manage all this and gain the trust of the industry, then I think there are plenty of options in a wide range of application fields where you can implement functionality into the parts. This is the whole trick with AM. There must be something smart and clever within the part, whether it is weight or cost reduction or the cooling channel functionality. And we have to search for these things, and then we have to prove that we can make them.
Yeah, I mean, that's very true. And I mean, Anna, you also mentioned it in the beginning, you are also often dealing with projects from the medical industry, which is basically the whole other end of the spectrum. Also very difficult in terms of certification, because you have to make sure it's not harmful to the human body, but also there in terms of the geometries, they are mostly printed already. It's kind of lattice structures or very complex shapes. So probably also interesting to see where or what are the next steps there.
Yeah, certainly. In the medical industry is another industry where we see, a lot of applicable things in terms of qualification that, at least, in my experience, really apply very well for an industry that, everything needs to be qualified and documented. There's a lot of really interesting, new products. I would say there are certain products that are quite well developed within the medical industry, and there's quite a good, penetration of additive manufacturing. But they're, new materials, and of course biocompatibility is, a really important topic. And this is where it's, also challenging as an OEM, because we have companies that are really concerned about cost per part, maybe service providers that, are not really concerned as much about providing parts to qualified industries. Then at the same time, we're trying to, develop a machine that's also suitable for the aerospace industry and for the medical industry. And so, it goes back to this challenge. Do we try to put all these bells and whistles on this one machine and package it to everybody? Because, different customers need different things. One good example is, AMS 7003, the aerospace powder bed fusion process spec. It's, very, very challenging for powder bed fusion OEMs to comply with this documentation, but it's also really important, right, when we're talking about qualified industries, and this has also pushed EOS to be able to develop a package where we can measure, a lot of the machine parameters that are required, but of course this is not kind of a standard package. So, there's, as OEMs, we have, a really difficult challenge to figure out, how can we best support all of these different customers? And sometimes that means developing these new software solutions, different additional packages, but, it always comes back to this cost per part and kind of how different industries can handle that if they're expecting the traditional parts that they would otherwise be printing, if these additive costs are extremely high and just doesn't even make sense to go with this technology. These are all things that we need to make sure that our machines are kind of appropriate and good solutions for all of these different cases.
And I agree. I think there are two totally different ways. I mean, there's certainly a big market for more universal machines where you can comply with a lot of industry standards in different industries, and that you can probably use for different industries as well. So if you do a job shop, you probably do not want to just be able to produce for aerospace, but in the future also go for energy sector, go for medical. But then there are also industries where probably, and where we already see that there are machines developing that are heavily specialized to just one certain application. So you go by all these really large Z-height machines. I mean, basically just coming from the fact that rocket nozzle has certain dimensions or a certain ratio of diameter to height, right? So,
yeah, true. But don't underestimate the large machines. I mean, also like heat exchanger applications are coming out of nothing. Not out of nothing, but we get to know customers which are asking for huge blocks for heat exchangers, like cubic meter heat exchanger. And it's kind of interesting that you then have this huge part with tiny walls as tiny as possible. Again, we come again to the point of reproductivity from these features at any point within the build envelope. And then you also need to have the right heat management, because if you build over hours or even days, so we have this one burner chamber on our booth, which was built on a single laser machine over 14 days, you have to ensure that the machine is running for the whole time in the same condition. And even with those tiny walls, the build job gets taller and taller, the heat level or temperature level in the part will increase. How to manage this while avoiding that the process might turn over and you get into troubles with defects or recorder crashes, things like this.
And I think that's probably also another way of looking at it, because suddenly you have this machine that is capable of producing really big parts, and then you find other industries that also can make use of it. And then you, from there, can take it and find even more interesting applications for something that you have developed and is working really, really well.
Exactly.
Good. Last try. Are there any questions from the audience to our panelists? Some aspects that we haven't covered yet? Yeah. Go.
What's the view of each of the panelists on, we talked about process monitoring and the importance of process monitoring. So what's the view of each of the panelists with regards to developing in process monitoring yourself as an OEM or using a third-party supplier? Because there's a few third-party suppliers out there, but also OEMs are doing their own innovation on process monitoring.
So I can probably repeat the question so that the audience can hear. The question was, what's the take of the panelists on OEM monitoring solution versus third-party monitoring solutions, and how to implement them into the machines?
Yeah, well, I would say from my perspective, of course, EOS want to provide monitoring solutions that meet the needs of the customer. Of course, that's not always the case, right? Like I mentioned, we have all these different industries. They're interested in different aspects there. Of course, at EOS, we're trying to develop solutions that are sufficient for our customers, that do meet their needs. Of course, that's not always the case, and especially in, additive is such a new industry, and of course there are always going to be third-party solutions that exist. Ideally, those will be integrated into the whatever the OEM solution is, so that we really understand what the third-party solution is doing, and making sure that it's really providing that quality improvement that you're looking for in the machine.
I think I kind of said this earlier, I think there's always going to be an inherent struggle to have a third-party solution be able to cohesively integrate into an OEM platform. That being said, at Velo, kind of the approach we've taken is we collect terabytes worth of data for every single build. And from our perspective, maybe it's just my perspective, you know, we can collect that data, but ultimately the end users will tell us what is important in that data. And so I think the most powerful thing we can do and what we're working on is getting that data out of our systems and into their hands to analyze. So not necessarily putting the onus on them to figure out how to monitor the process. We have all that built in, but what to do with the data that comes out and figuring out how to connect that data, those trends, back to part quality, repeatability, hopefully reducing NDT and all those types of things. And I think from the OEM position, again, like we can put all the hardware in place to collect the data, but we need the industry to tell us how to use that data and what is most valuable within that data set. And that's not an easy ask by any means. I understand that.
I think we as AMCM play a little bit different role here. First of all, of course, we use all the technology which EOS is providing. So if EOS is developing monitoring on their own or with partners, we will apply this. But it is actually our task to also implement things into this machine if the customer has an idea and wants to have a new tool in the machine. So if there is something new on the market, or a university, for example, has an idea, what could we do to improve monitoring? We might be a very good partner to actually create this link between something new and the machine. It's not so easy for bigger companies which target with their machines like a serial machine production for then serial use in the industry. We have this different approach to say it's the first of its kind maybe. And if there is a first of its kind for monitoring, we will link it with the machine as good as we can. And then we work together with the customer to see if this connection has, again, this potential, this usability, functionality, and if we need to improve something. Yeah. This is maybe a little bit different role in this whole industry, that we are open for any crazy idea which is out there, and then we hope that we can help within a new machine project to make this happen.
Yeah, first of its kind machine, so to speak.
It's the Frankenstein machine sometimes. It is.
Thank you very much. Then probably, yeah.
I have one question. So I came from your booth over to here and saw that you actually have the nLIGHT laser integrated into one of your machines. And I'd be really interested actually just to hear like what it has enabled in that space, and like what going forward you think you could still get out of it, because I don't think it's been integrated for a very long time.
Okay, so
when you talk about the Frankenstein machines, any insight into that?
I might repeat the question. He was asking, so there's an nLIGHT machine running on our booth, or an M290 machine equipped with this nLIGHT laser, and how this all came together basically, and where it might go. So my colleague started to work with the company nLIGHT maybe since 2019, I guess. So first of all, you get in contact, you specify the laser. It's not only the laser itself, it also matters what kind of machine concept you have, your focal length, what kind of scanners and optics you might want to use, and what your desired beam quality and shape, size on the target, on the build plate might be. With this initial specification, both parties then start to develop and see if the developed laser and the developed machine work together. We installed the laser in, I think the integration of the laser started in 2020, 2021, the first test happened. Originally we started with a different size of the laser spot, which was arranged on our side with the laser scanner and optics, or mostly scanner and optics. And we re-evaluated this and arranged different spot sizes then. And it could happen that you start with your parameter screening with certain spot sizes and you have a decent, nice preliminary solution. But for other reasons, you change the spot size and you work it over again. And already now you see that this is not ready to hand over to industry maybe. You have to freeze in a certain stage where you rely on, where you say this will work for the next couple of years. It's worth for a company to apply this, qualify it, and freeze it in because it has enough advantages to work and live with this for quite a while. And to prove this is now the challenge.
What were those advantages?
I might repeat myself a little bit maybe, but you can target for quite a lot of things here. Our first initial target was increased build rate, productivity. This is easy to understand. You can create impressive numbers. It's attractive to the industry because in the end it affects your business case, hopefully. And so targeting for this, you can go for quite some ways. You could increase layer thickness. You can target build speed remaining a standard layer thickness. So what you see in the machine running on our booth is a standard 40 micrometer process. The build rate is this theoretical cubic millimeters per second, 12 cubic millimeters per second, and we were coming from 4.2, 5.2. So it's a step forward. The nice thing with this 40 micrometer process is it fits into the existing processes, so we can apply all the existing upskin, downskin contour parameters. And you have to think in these clusters. If you want to productize it, find a way to implement it fast, make it useful, make it understandable for the customer as well. So it shouldn't be if you try to gain all the advantages at once, you might end up with something which is just not handy for anyone to apply. That's the challenge here.
Good. Then probably one last question from my side to close things off here. So we are now here, 2023 Formnext, probably also to have some perspective in the future. So how do you see, or what do you see as the highlights, the innovations happening in 12 months from now? And if we probably meet again next year, what has happened, or where do you see the AM industry coming, or probably also some wishes how it should evolve?
Yeah, on my wish list, so of course we mentioned before, every 12 months we have new machines, new lasers that we're packing in machines. Of course, we have Formnext every year, and trying to develop these solutions at Formnext. On my wish list is the next 12 months. I see a lot in various different industries that qualification is always still a topic, and of course this will always still be a topic for customers. My hope is that we have our machine OEMs, all the developments that we're producing on our machines, that we can continue to improve how we support our customers doing qualification. So at the same time, we have industry partnerships and industrial learning groups, ASME, ISO, ASTM F42. We kind of need to have a convergence of all of these technical specifications that we're creating and now the machines, and I really hope that we can continue to marry these two together, because this is what I continue to see as a challenge. So we come out with a new solution and people say it's not qualified or we're not ready for it. We're not ready for it, that we need to stop. We need to make people ready for these solutions, and so it's both of these, the push and the pull, and so I hope that qualification will continue to be something that we can solve.
Great.
Yeah, so I agree, and I think add to that of, my hope is that we move away from these kind of one-off wow demo parts to real production applications. I would love to see a step change and production adoption of metal additive manufacturing. And I would love to see this floor just littered with people using it for parts that are in real use in life. And I think that will do great things for the whole industry, and that comes back to standardization and again, repeatability and being able to deliver what any other manufacturing technology would do. So yeah, in my mind, my wish list is like, people stop looking at this industry as this like snowflake R&D cute technology and as a real manufacturing technology.
As a former US product developer, I agree 100%. Yeah. Now in this different role with AMCM, of course, we are also looking into the make new things happen, which don't necessarily need to be qualified within 1 year. We are happy to partner with institutes and university, maybe place the one or the other M290 machine with nLIGHT lasers there. We started to implement the nLIGHT laser into dual M290s, so one might think about what can two lasers do with interaction, start these things. This is far away from any qualification. It's enabling technologies. And we are wondering what smart people all over the world might bring out of our machines with this nLIGHT laser or other tools like extended build plate heating or whatsoever. Our only problem is that we are a fairly small part of the company when we can't do it all on our own. And yeah, we are looking forward to partner up and see what smart people can bring out with these interesting tools.
Yeah, very good. Thank you very much, guys, for making the time, for having this great panel discussion. Thank you, everyone from the audience, for taking the time, listening, for asking good questions. I mean, I will stay a few minutes at the booth. Probably other guys will also have 1 or 2 minutes left. So if you have any pressing questions,